All right, in this question, we're looking at a constant potential difference is applied between two horizontal metal plates. A charged oil droplet is held stationary by the electric field between the plates. As some of the oil evaporates, the droplet loses mass and starts to accelerate. Its charge remains constant. In which direction does the droplet accelerate, and which change needs to be made to the separation of the plates in order to stop this acceleration? And so this question was really a good one to sort of emphasize some of the ideas we were talking about in class about Millikan's famous oil drop experiment. The oil droplet has mass, and if it has mass, then it has weight, and that weight vector is going to act down this way, so it has weight mg. In order for this to be held stationary by the electric field, that means that there's going to be an equal and opposite charge this way, right? And so that's the electric force that's acting on the charged oil droplet. Remember that in between these plates, there's an electric field. An electric field is a region of space where charges are going to experience a force, namely an electric force. And so when those forces are balanced, the droplet will float. But now, as the oil evaporates, it loses mass, and that means that its weight is going to decrease. And so as this thing is evaporating, sometime later, the weight vector is not as pronounced. Well, if we don't make an adjustment to the electric field, that means there's going to be a net acceleration or a net force upwards, and we know from Newton's laws that things accelerate in the same direction, a net force is applied. So it still has some weight, but the force acting up is stronger, and so it's going to accelerate upwards. And so either choice C or D is correct, just by thinking through sort of the idea of it losing mass and the weight vector becoming less pronounced. We know that there would be a net force upwards and therefore acceleration upwards. So in order to stop that acceleration, we need to do something to the separation of these plates. We need to change how strong the electric field is. The electric field is the force acting on the charge, and because it says that the charge remains constant, right? It says its charge remains constant, then we know that as we sort of decrease the electric field strength, we'd be decreasing the force, right? Directly sort of proportional to it. And so we need to somehow decrease the force by decreasing the electric field strength. In the laboratory, we can adjust the electric field strength by either changing the potential difference between the charged plates or the distance between them, right? Those are the two things that we're sort of in control of in the laboratory. They tell us that the potential difference is constant, right? So we're not changing this, we are changing the separation of the plates. In order to decrease the electric field strength and thereby decrease the force, the electric force acting on the charged oil droplet, we need to make an adjustment by increasing the distance between the plates, right? By dividing by a bigger number, we decrease our electric field strength. And so choice D agrees with that. The acceleration is upwards and the separation of the plates has to increase in order to stop the acceleration. So choice D is correct.